Let V be a vector space, and let V1 up to Vk be a set of vectors in V. We're going to show that the following are equivalent. So the first statement says there is no I among 1 up to k such that Vi can be written as a linear combination of the remaining vectors. The second statement is lambda 1 up to lambda k equals 0 is the unique solution to this equation here, lambda 1 times V1 plus all the way to lambda k times Vk equal to 0 vector. And here, lambda 1 up to lambda k are scalars. So these two statements are equivalent, and here's why. So we're going to first show that 1 implies 2. And we're going to do this using the contrapositive. So we're going to first assume that there's a solution with not all the scalars lambda 1 up to lambda k equal to 0. Suppose that lambda 1 prime plus lambda k prime Vk is a 0 vector for some scalars lambda 1 prime up to lambda k prime such that lambda I prime is non-zero for some I among 1 up to k. Alright, so assume that statement 2 is false. We're going to show that statement 1 is also false. So suppose this is non-zero, then what I can do is I can write lambda I prime Vi as the remaining. But now this means that since lambda I prime is non-zero, I can multiply both sides by 1 over lambda I prime, and that will give us this. So this is actually k, not n. So k here. And if you look at this, I have written Vi as a linear combination of the remaining vectors, right? Because Vi is not going to appear on this side. So this shows that statement 1 is false because there is some I such that Vi can be written as a linear combination of the remaining vectors. So this direction is proved. Now we're going to prove the other direction. So I'm going to prove that 2 implies 1. And again, I'm going to prove the contrapositive of this. So I'm going to show that if 1 is false, then 2 is also false. So 1 is false means that there is an I such that Vi is a linear combination of the rest of the vectors. So that means it can be written as something like this. But now if you look at this, we'll see that we have a solution to this equation here that doesn't have all the scalars equal to 0, because I can just take, for example, all the lambdas equal to the negative of all these alphas except for the index I, and for lambda I just take 1. That will give me a non-trivial solution because lambda I is not 0. And this completes the proof that statement 1 and statement 2 are equivalent, and so we have equivalent ways to define linear independence.